All right, welcome to the 9th lecture in mathematical finance. So as we started last time, we want to study today the general connection, or start studying the general connection between Martingale measures and the notion of no arbitrage. And this is just to recall what we started last time, section 3.3, called no arbitrage. And Martingale measures. Right, so just to remind you, we have seen in the binomial model with one trading period that the market is arbitrage free, basically if and only if the discounted price process is a martingale under this measure Q. So this was called then Martingale measure. And now we want to investigate this relation in the more abstract general setting in discrete time. All right, so today we leave the binomial model and we consider general. So this means okay, it's not the binomial model, it's a general discrete time financial market. Fulfilling our usual assumption that we have one risk-free asset, which corresponds to the bond market, and then we have a number of risky assets, which are the stocks and shares on the market. And what we have seen last time is that a crucial role in this investigation we're going to do now are the discounted objects, so the discounted price process and the discounted value process associated to trading strategy. And this was our motivation to introduce some more mutation, namely the discounted counterparts of the objects we have already defined. So discounted price process will be denoted by S tilde. And of course, it's still a stochastic process indexed with respect to our discrete time set T, consisting of D assets, right? Is given by, well, obviously, so we define the price of the asset at time T by the bond. So that's for T, our index set, and we have D assets, so for I equal to 1 up to D. So that's so just to remind you, this is your discounted price process. And then we also have a very convenient short writing, which will pop up, is the, well, was a different operator, which tells you the price changes over the T trading period of the discounted price process. So this delta S tilde T is just the, by definition, the difference of the discounted price at time T minus the discounted price at time T minus 1. And this is well defined for all T, of course, without time 0. Right? So this is the price movement of the T trading in the T trading period. Okay, as a first step, before coming back to the Martingale measures, we wanted to understand, how the objects now behave if we consider them with respect to the discounted quantities. So this was the last thing we wrote down last time, namely lemma 3.10. So, which was telling you if you have a self-financing trading strategy, phi consisting of our position in the risk-free asset and in the de-risky assets, we can represent the discounted value process associated to this trading strategy phi. Discounted means we discounted by the risk-free asset, and this is just equal to what you expect somehow the initial capital we have, so the capital at time 0, plus the gains we make in the trading periods up to time t, then we sum them up. And so that's the position we have in the market at time t minus 1. So this is the position we hold during the t trading period, and these are the discounted gains we make by holding this position. All right, and now let's come to the U part. So this is what you have already seen in the last lecture, but we haven't done the proof. So this is where we start today. Let's prove this little lemma, also to familiarize ourselves again with the definitions. So what we want to do is, okay, let's consider here some k in index set without 0. So what we observe is if we consider the discounted value process at time k minus the discounted value process at time k minus 1, well, let's plug in the definition of value process. So this is the discounting factor k. So this is the discounting factor, and what is now the definition of the value process at time k given phi? Well, this is just what we buy at time k. So this is beta k plus 1 multiplied with bk plus value ak sk and now minus discounting factor bk minus 1, now the same. This is beta e plus alpha k sk minus 1. No space. Sorry. Yes. All right. So this is, as I said, just the definition of the value process. Now we use the self-financing condition, right? This is the only condition we have given here in this lemma. So let's use self-financing, which tells us what? That the position we choose here at the beginning of the kth trading period is equal to the position so the value we have here is equal to what we had at the end of the kth trading period. So right. So this is here, going from here to here is self-financing. And now we keep the second part unchanged. Plus AK. Right. And now we see what's going to cancel here. Well, this discounting factor and the value at the risk-free bond, they cancel, and the same happens here for the second term. So what we get is beta k minus beta k. And now we put together the things we have here in the risky asset. So this is an AK, alpha k in both terms, so we can pull it out. Now we have here the difference between SK divided, so discounted by BK, and the same just 1 times that earlier for SK minus 1 and BK minus 1. Right. All right. And now what does it is? This is obviously equal to 0. So we have here A alpha K. And then here we have the discounted price process. This is the price change of the discounted price process over the K trading period. Okay. Well, now if we want to express this discounted price process at time t, well, we can use a telescoping sum argument, as we have done several times already in this lecture, to express this as the changes over each trading period in our discounted value process. And K minus 1 and here K. And now we use what we have calculated here. So this change of the discounted value process. Right. So here to 0 is equal to 1. So the discounted value process at time 0 is equal to the value of at time 0 without discounting. And then we have here, by our small calculations we have already done, that this is equal to the sum of from k equal 1 to t of alpha k multiplied with the changes of the discounted price but in the k trading period. Right. And this is already all we wanted to prove. So what we see here is that we can express the discounted value process on the left-hand side in terms of the gains we make by investing in the discounted risky asset or price process of the risky asset. Right. So I already have used the word discounted value process. So let me also link it to a formal definition here. So if we have a trading strategy, as usual, phi consists of two positions, right? The one in the risk-free and then the risky asset. And well, that's the trading strategy. And let us introduce now the discounted value process associated to this trading strategy, of course, which we denote by B tilde. We define it then by, well, so what we do is we discount the value process with the risk-free asset, and well, this is nothing else but definition of the value process without discounting, right? If we discount the price process, so the risk-free asset with the risk-free asset itself, we get here just a 1, and then the discounted risky for T. Without T. Right, this formula holds only if we take, I mean, this formula was only defined for T less than capital T. So we need to make another definition, which is here. Right. All right. And let's make a second definition, namely the discounted gain process. That feels better. Namely, gain process. So these are the gains or losses we make by trading with respect to phi in the underlying market. All right. So gain, of course, at time 0, there are no gains, right? So the gain process, if we trade with respect to the trading strategy phi at time 0 has to be 0, right? At time 0 we couldn't have produced any gains. And now gain at time t, if we trade with respect to phi, is the gains we make in each trading period by trading with respect to alpha. Right, so that's 4.0. Okay, so that's discounted gains. So I'm not using here the tilde as I usually do for discounted processes, just because we are never considering the gain process without discounting. And this makes my notation then easier. All right. First thing we want to do is, we want to understand, what happens to our definitions we already formulated for the undiscounted objects with respect to the discounted ones now. So we want to understand, I mean, what self-financing means in terms of discounted quantities. So let's consider trading strategy. Trading strategy. Okay, then the property of phi being self-financing can be equivalently formulated with respect to this discounted price process, which means phi T is equal to, so this means, as before, self-financing was telling you that you always just rearrange your position, but you never withdraw or throw away money. And this is the same here, just formulated in terms of discounted price process, right? So you consider it the discounted value process and you see you're not throwing away money or withdrawing it. Okay, so again, an easy proof. Of course, we have to do it. So let us recall what self-financing means for trading position. So trading strategy was called self-financing. This is just the definition. This is that if we have that the money we hold at the end of the teeth trading period equals the money we have at the beginning of the teeth plus one trading period. So this is just the definition of self-financing. T equal 1 up to t minus 1. And now, since our risk-free asset is assumed to be strictly positive, we can multiply this by 1 over bt. So we discount this quality here with our risk-free asset. If we do this, this is an equivalent reformulation. So that's t x1 equals to this discounted. Well, and what we observe here, this is just the discounted price process. So if we reformulate this, this is II. Okay, so the condition of still being self-financing can be equivalently reformulated in terms of discounted objects, or in respect to discounted value processes or discounted price processes. Okay. The same is true for the notion of arbitrage or no arbitrage. And this is just formulated in the next lemma. So again, let us consider a trading strategy which is supposed to be self-financing. Self-financing trading. So what are our equivalent formulations? The first one is phi is arbitrage opportunity. So it's a way to make money without risking to lose any money. This is equivalent to saying, well, I start with initial capital, which is less or equal than 0. And now the discounted value at time, the terminal discounted value I have is always almost surely non-negative. And with a positive probability, the discounted value I have and the terminal time is strictly positive. And this can be again reformulated in terms of the gain process. Meaning, so I start again with a capital which is less or equal than 0. My gains or losses I have made up to the terminal times are strict and non-negative, and with a positive probability at the terminal time I have made some gains. Okay. Let us prove this. I mean, this is again not really hard, but of course it has to be proven. So let's look here at the proof. Again, let's recall, I mean, like we have done for self-financing, let's first recall the definition of an arbitrage opportunity. So it's actually very nice to recall all the central definition, which will follow us through the whole course. Let's take here a minute. So again, this is just my definition. So some trading strategy, so some self-financing trading strategy is called arbitrage if we start with a non-negative amount of money, but at the terminal time we end up with a we start with a non-positive amount of money, we end up with a non-negative amount of money, and with a positive probability we really made some gains. So with a positive probability, the terminal capital we have is strictly positive. Okay. Now again, so this is equivalent. We can divide by our strictly positive prices of the bank account. So at time 0, 0. Or this is the same. So we have here the discounted one, and so we divide by something strictly positive, so the inequality signs are not changing, and we have exactly the same condition, which was our first equivalent characterization. And for the second one, we just need to relate the discounted price process with the discounted gain process G. And well, as we have here a self-financing trading strategy, we can apply our last lemmas, lemma 10 or 310, which we're telling us, let's go back. That's this one here. So we're just telling us the discounted value process is given by the initial capital. And so now we can, so this here is just discounted value process at time t, and this here is the discounted gain process of phi with respect to phi at time t, right? So let us use this observation here, and it tells us, so we apply this observation to the terminal time t. So the discounted value process at time t is equal to the initial capital plus the discounted gains up to time at time t. Right? So this is like a side of, so this means if we apply this, we can go from here to here. Again, reformulating it in an equivalent way as, well, that's initial capital. Well, we started with initial capital negative, so that's K. And finally, with a positive probability, we end up on positive. All right. All right. Okay. So much about the discounted properties. And now we want to finally come back to the Martingale measures. So we have defined the Martingale measure, or said that this measure Q in the binomial model is called Martingale measures, but now we want to turn this observation into a general definition. And this is done in the next definition here, 3.14. So let's consider a probability measure Q, and it has to live on our measure space omega f, right? We want to compare them somehow. And now we call this measure Q Martingale measure. And well, sometimes it's also called risk neutral measure. If the discounted value process, so as tilde, is a d-dimensional, right? This is a d-dimensional process, Martingale. Right, what does it mean? I mean, d-dimensionals, of course, under the measure Q. So what does it mean here? D-dimensionals, that just means that each component of this discounted price process is a Martingale, right? So if I take the conditional, if I take the expected value, the absolute value SI, but the prices are positive anyway, so this is just the price, the discounted price process is integral with respect to Q. And well, this is the same as this, just recall this, we have non-negative prices, but let us keep the definition of a martingale. And if I take the discounted price process of the ETH at time t and condition it on the filtration up at time s, I just get the discounted price process at time s for st in our index set s is less than t, and of course e can be between 1 and d. So that's all right. So that's our martingale measures, and sometimes also called risk neutral measure, because under this measure Q, you have a risk neutral perspective on the market. This means under the measure Q, the discounted price process is a fair game, which we formulated into terms of martingales. So this means in average, you make gains and losses at the same probability. So I mean, this is not true because you take the expected values, you know, but I mean, this basically tells you under this measure Q, so if you take the perspective on the real world, that Q's the probabilities assigned to the events, trading the market is a fair game. Now, another definition, of course, in the end, we don't want to take any martingale measures. You care most about the martingale measures, or we care most about the martingale measures, which are equivalent to the underlying measure P, right? So we started with the modeling our financial market, which was given by a probability space omega fp, and we want in the end to consider these martingale measures which are equivalent, so which see the same sets as the original measure P. So we call the measure equivalent martingale measure, and we use the shortcut EMM if Q is additionally equivalent to the measure P. Okay. All right. So that's right. Right. So let me know also. Yeah. But let us also define, so we need them later, the corresponding sets. So first thing is we define the set M of all martingale measures. So this Q is martingale measure on our measure space omega F. And secondly, M star are all those Q's in which are martingale measures and they're supposed to be equivalent to our underlying measure P. And in this context, also the measure P, which was our underlying probability measure, has name. So here P is referred to as the physical measure. So this, so currently, I mean, well, you observe here two measures. The one is what we start modeling our financial market, which is the probability space omega fp. So there is somehow a measure involved which assigns how likely certain price movements are. And well, so this is basically the God-given measure we decided we want to have on our financial market, or how we want to model our financial market. And then there are other measures which basically come out of the theory here, which are the Martingale measures. Okay. Yeah. And I mean, along the way in the course, we will understand better and better how important Martingale measures are. Okay. And again, so we can also formulate now the notion of arbitrage in terms of this equivalent Martingale measure. Right? So 3.16 is, okay, if we have our general financial market, so let me call, so this is as before our financial market. And well, just to make it here explicit, so this market is modeled on a probability space omega fp. And now we can take a measure Q, which is supposed to be a Martingale measure, and it's supposed to be equivalent. So we take a measure now from this set M star, which are the equivalent Martingale measures. Then phi is arbitrage, and then this is actually, if we look in the definition, was defined with respect to the measure P. Now this is equivalent to saying, well, this is an arbitrage opportunity. If we equip the probability space, or if we replace the measure P by the equivalent Martingale measure Q. So the notion of no arbitrage is actually stable under equivalent measures. I think this will become rather clear if we look at the proof of this lemma. Let's the proof. So let us recall what equivalent equivalent measures are. So Q, P are probability measures. On our measure space omega, right? And now Q and P are equivalent. by definition, this is right. This is the definition of being equivalent. Means Q is absolutely continuous with respect to P, and P is absolutely continuous with respect to Q. So this means if I have a null set under the measure P, it's also null set under the measure Q. And if I look at the second condition, this means if I have a null set under Q, it's also null set under P. So in other words, for all events in our sigma algebra F, we know Q of A is 0, so it's a null set, if and only if P of A is 0. So that's just the definition spelled out of equivalent measures. And now let us recall. If we start the definition of arbitrage opportunity, so if we have a trading strategy and we have to assume it's of course self-financing. This is part of the definition. Such that what's an arbitrage opportunity? This means we start with initial capital less or equal than 0. It's non-negative, P almost surely. Right? And here I want to be careful for a moment, because this is the main point. And with a positive probability under P, we are strictly positive. Right? This is now equivalent if Q is equivalent to P. If we replace here the P, because the null sets where this is not true also null set under Q, so we can go over to the measure Q. And well, if an event has a positive probability under Q, it also has to have a positive probability under Q, since they're equivalent. So this is, again, not super hard. So here we are. We can reformulate the notion of arbitrage opportunity with respect to P now with each equivalent measure Q. Now, actually, this is actually not needed, so this is okay. Let me make this to an example. This is not correct, so this is correct, but I want to have more general here. And Q be an event measure, and probability measure. So Q and P are equivalent. For example, this is the main measures we are considering. Q is in this set M star of equivalent Martingale measures. Right, but this is, I mean, as you see here in the proof, is not needed for the proof. Oh, and for the statement of the lemma. All right. Okay. So now let us characterize the Martingale measures in terms of discounted price processes. This is the contents of the next proposition, um, 3.17, which tells us well. So let us start with considering a probability measure on our underlying measure space. So that's omega f. And now we have equivalent conditions. So following conditions are equivalent. The first one is, well, M is a Martingale measure. The second one is to say, well, if I consider a trading strategy phi, and this is a trading strategy, and I want that this is self-financing and bounded. Then this implies that my discounted value process associated to this trading strategy is a Martingale. Under Q. Okay. The third one is, well, if again I have a trading strategy which is, I don't want to trade only with bounded trading strategies, so I want to have this more general, is self-financing, and if I look at the associated so if I look at the expected value under this measure Q of the discounted value process phi, and then I consider only the negative part, then this has to be finite. This is my assumption. Then the discounted value process is again a Martingale under Q. And so you see, we have now dropped the assumption of phi being bounded. So our trading strategy is not necessarily any more bounded, but we have replaced it by the condition that the negative part of the associated discounted value process is integrable, right? So just to recall it, so this definition, so if I have a random variable x, and I want to consider only at the negative part here, this is defined as the maximum of x minus x and 0. Right, so this is not part of the statement. This is just for you to recall the definition of the negative part. All right. And now I can formulate this even more general, or even weaker. This is done in the next condition, which is condition 4. So again, if phi is a trading strategy, and I want to assume that it's self-financing, because this is what we care about, And the associated discounted value process is negative here, Q almost surely. And then this implies that the expected value under Q of the discounted value process at the terminal time t is equal to the initial value I started with. So phi v0 with respect to phi. And that, I mean, all these three are equivalent conditions. So we can fully characterize the property of a measure being a Martingale measures in terms of the behavior of the associated discounted gain processes if we always assume they are self-financing. Right? So basically, if there are martingales under this measure, so if all discounted value processes are martingales under this measure Q, this means the measure has to be a martingale measure. All right. So this is the main work for today, is to prove this proposition. Okay. Okay. So we start with the first equivalence, which is the equivalence between one, so I and II. So what we want to show is we want to show that equivalent for the measure Q being to be a Martingale measure. It's equivalent that the discounted value process is a Martingale under Q for every self-financing and bounded trading strategy. Okay. So let us recall that since phi is self-financing, we can represent the discounted value process at time t in terms so this is, so we can represent it as the initial capital we have and then our gain process. So this is discounted gain process, right? And this was, if you want to check it in your notes, so this is what we proved at the beginning. Today, this is lemma 310. So why do we want to recall it? Well, because what we see here that's nothing else than alpha as tilde at time t, right? So this is here the discrete characteristic integral we already investigated. Okay. So, well, why do I care about this? Because now we realize, wait, if they consider self-financing trading strategies, we can represent the discounted value process as a discrete stochastic integral. And now we see that we already have proven the first equivalent here, namely in our section about discrete stochastic integral. So this is the content of proposition 2.3. Which was telling us, okay, something is a martingale, so the integrator is a martingale if and only if the corresponding discrete stochastic integral is a martingale for all predictable and bounded integrals. Okay. That's good, because here we have already done all the work we need, so we can go to the next step. Make a circle argument. So next we want to prove that I implies 3i's. All right. So what does this mean? So we want to show that if we know that for every self-financing and bounded trading strategy, it immediately follows that the discounted value process is a martingale and a Q. We can also show that if we have a self-financing trading strategy for which the negative part of the associated discounted value process at the terminal in T is integrable, then we already know that it's a martingale. So the discounted value process is a martingale under Q. Okay. So this is a bit more work to do because, well, we haven't done it yet. So let us start with the observation. So if we want, let me recall it. Right, so what we want here is we want to start with the self-financing trading strategy, beta and alpha, and they are assumed to be right, so this is assumed to be self-financing, trading strategy with okay, the negative part of the associated value process at the terminal time under Q has to be integral. Right? So these are the condition we have here. If you look at 3i's, right, this is here our assumption, and now we want to show that this, if we assume 2i, then this is a martingale. The discounted associated discounted value process is a martingale. All right. So let's check this. And the first claim I want to show is following. So this is claim, which is so if we know that the value process discounted one under Q, and I at time small t, the negative part here from is integrable, and then I have the martingale property for this step. This means I look at the discounted value process at time t, and I condition it on ft minus 1. That's nothing else than discounted value process at time t minus 1. Let me call this to be consistent with the lecture note 3.6. Okay. So first thing, we want to prove this, and then we want to follow the Martingale property. All right. So how do we proceed this? First observation is, okay, everything is well defined. So as and this is integrable, so that's a tilde here. We know that the conditional expectation, even if this does not mean that we are at least not yet clear that this is an integrable random variable, we know that this is well defined. Okay, because we have a bound on the negative part. So by this was remark 2. So because if we can bound the negative part of a random variable by an integrable object, then we have a well-defined conditional expectation. Okay. Okay. So at least the statement I was writing here a priori is well defined. And now let's check that this is also true, what I claimed here. So let us define this is the alpha. So we modify our trading strategy alpha to alpha C T, which is our given trading strategy alpha, and we restrict it by assuming that alpha has to be less than C. Oh, to the event that alpha is less than C. All right. For C is some constant. All right. So what we do is now we take our given trading strategy and we constrain it on the event to be less than C in order to achieve a bounded trading strategy. Okay. So this means alpha CT. If you look now at this discrete integral here, is a Martingale in the Q. Right? Because now we can use the second condition as we have a bounded under Q. So, right. Well, and if this is a Martingale, what do we know? Well, if we look at the expected value, and they take the absolute value around it. So since this is a Martingale, this has to be finite. And this here, game process has to be Martingale. So that's, if you condition it on the filtration at time t minus 1, this has to be 0. Okay. So now, how can we use this? Well, we want to show that if we consider the conditional expectation under Q of the discounted value process, the conditional expectation with respect to ft minus 1, we want to show, and this is the claim, that this is equal to the value process at time, the discounted value process at time t minus 1 of phi. So this is property 3.6. All right. So first thing is using here definition. So that's nothing else than, right? Because otherwise this is 0 anyway. So all right. Here we are. Minus so condition that's 1 plus, oh sorry, minus phi alpha ct ct. Sorry. Let me redo the calculation because I missed something which, wait, okay, this was, and there's actually one main point missing here. Right, so I missed. So if I consider this conditional expectation here, and now I have to add my alpha minus t, otherwise, of course, this is not right. And now this is, right, this is measurable with respect to, so this is ft minus 1 measurable, sorry. So I can pull it in, then we have the equality here I claimed. Conditioned on ft minus 1. And now I can subtract or add the 0. So I subtract the 0 here. Right, this is just 0 because this term has a martingale. Right. So this, let me make it like this. So this is just 0. Now I can pull this term in as well. Okay. This is, well, if I subtract the gains I made in the t trading period, I end up with the value process at time t minus 1 of phi. And of course, here everything restricted to the event that alpha t is less or equal than c. Right? And now, well, this is again ft measurable, and for this step, I mean, these both are ft minus 1 measurable, so I can pull out the value, discounted value process at time t minus 1 of phi, and I can pull out the event, the indicator of set of the event that alpha t is less or equal than c. So this is again here, you make it a different color. So that's here is ft minus 1 measurable. Okay, that's good. Because now the only thing I have to do is sending c to infinity, right? Then this goes to the old set omega, and this goes to the entire set omega. So yields our claim. And this is the claim I made, that I have basically the Martingale property in the teeth trading period. All right, and now I change the color. Now the question is, why is the condition I assumed here true? So, okay, let me come back. So now the question is, why is this true? So why do I get the Martingale property in the teeth trading period? Well, let's check this. So that's the end of the claim, the proof of the claim. And now if we use, so for the last trading period, we already know that it's a Martingale, because at the beginning, so we assume here oh, sorry, here's the minus missing. Okay. So for the last one, it's true. So the question is, how do we get the other ones as well? Well, now let's use our claim. So if we look at the negative part of the discounted value process at time t, capital T minus 1, so the negative part, then this is nothing else. So this is the tower property. So you have seen several times already. So right, for this time, I mean, for this, I can use my claim, right? And now, well, this minus here is a convex function, so I can use Jensen's inequality. Which tells me, well, that's nothing else than qt phi minus, and then the tower property allows me to get rid of the conditional expectation. That's by assumption less than infinity, right? So let's repeat this argument. It allows me to show that the expected value under Q of the conditional of the discounted value process v at time t, then the negative part of this is integral, which by our claim means that it's a Martingale in this step. All right, so that's good. All right, and this holds for all t and t. Okay. But now, I mean, we're almost done, but not quite yet, because we need to ensure the integrability property as well, right? So we have the defining property of a martingale, but what we also have to check is that it's an integral process. So let's do this next. What we know here is that actually this is true, right? But this is just iterating just a telescoping argument using the line above here. So what do we get if we want to show that the value process, the discounted value process with respect to phi is integrable? Well, now we decompose the absolute values into the positive part. So that's the positive part. We subtract the negative part here. And then we have to add the negative part again. And so this is actually the first expected value here is just the expected value of the positive part of the discounted value process, and then plus the negative part gives you the absolute value. And the nice thing here is, well, this is fine, right? All right. And this implies now that phi at time phi is indeed a Martingale. All right. Okay. Okay. One. I think I need an extra page. So I think before the end of the lecture, we at least can prove one of the implication, and this is the 3 i's implies 4. So what we want to show as the last thing for today is, well, if we know that for every self-financing trading strategy where the negative part at the terminal time is integrable, then we can show, and this is what we're going to do, is that if we have a self-financing trading strategy with terminal wealth, associated terminal wealth to be non-negative under this measure Q, then the expected value of the terminal discounted wealth is equal to the initial capital. All right. Okay. So how do we see this? Well, we made our assumption that the iteration at the time 0, so at the beginning for a market, is a trivial one. So what we know is if we have a martingale, which is a martingale. And why do we know this? This is so if you take a self-financing trading strategy which has at the terminal time and non-negative associated terminal, well, this implies, of course, the condition that this the negative part, which is just 0, is integrable. Erase this again, and let's go back to the proof. So if we look at this, as equal to, right, because this is a Martingale. Sorry, because our filtration is trivial, we have this identity. So the conditional expectation with respect to the trivial sigma algebra is just the conditional expectation. And this means we have this. And so this is Martingale. This is property condition, sorry, phi sorry, this is exactly what I wanted to leave away. And this is what we wanted to show. Phi. Right. Because now if we have, it's already late in the lecture, so if we have a self-financing trading strategy, which non-negative capital, we know by the proposition 3i that it's a Martingale under Q, and we want to show that the conditional expectation, so that the expectation under Q of the terminal discounted wealth is equal to the initial capital wealth, and this is exactly what we got here, which tells us if we have now the Martingale, we have these equalities between the initial value and the terminal, and the expected value of Q under Q of the discounted terminal. All right. Since the last step is again a bit longer, so that this property implies that this is Q has to be a Martingale measure, is where we start next time. All right, thank you very much. And well, see you next time.